In the field of evolutionary robotics, we use simulators to help test and verify robotic systems and adaptive control designs. However, the complex nature of many controller behaviors can make the algorithm hard to analyze and fully understand. Sometimes it leaves the following questions unanswered. What parts of either the controller, morphology, or environment is making this robot successful? Why did the controller make that decision in the first place? In our project, we created a three-dimensional simulator to help benchmark artificial intelligence and evolutionary algorithms. The idea is that we have a three-dimensional cube-like world where agents are required to move and morph into different rectangular shapes in order to overcome a set of obstacles. The transition between the simple rectangular shapes versus the complex legged systems will help simplify the mode switching problem. Specifically, it helps in the understanding of controllers that transitions between different gaits. As you can see, the blue object is our simulated robot or agent, while the gray objects are the obstacles within the tunnel world. Our agent is a 3D square-like object with associated discrete x, y, z coordinates and a length, width, and height value. The changing red and green lines represent sensory information being sent to the controller of the agent. These are each sensor objects attached to the agent. This information can help with the decision-making of the controllers. Each time step, the agent can choose to either move left, right, up, down, forwards, or backwards, or choose to morph into a different shape with approximately the same volume. Now that you know a little bit about the simulator and how the agent interacts with the environment, let's talk about the program controller we see on the screen right now. This will help us get a better understanding of how the simulator and the controller interact. Starting out, the agent randomly moves around until it finds a gap. The agent will know that it's found a gap when two of the sensors are flagged as green. Depending on which sensors find the gap, it will morph appropriately to fit through the openings while moving in the direction of the triggered sensors. Once all the sensors are clear, the agent will pass through. Let's illustrate that. In this example, the agent knows that the left two sensors are clear, so it will narrow its body and move towards the direction of those two left green sensors. Now that all the sensors are green, the agent will continue to move forward until it reaches another obstacle. The agent will repeat this process until it's finally reached the end of the tunnel world. Let's fast forward through the rest of the simulation with this in mind. Oh, and one important note to mention. This current controller on the screen is definitely not an optimal solution. It is simply a proof of concept for this simulator. With that in mind, please enjoy the rest of the simulation. The very next step is to implement controllers controlled by artificial neural networks. This is currently a work in progress. Using deep learning techniques, we are eager to see how the AI will perform. More than likely, it will outperform the current manually programmed controller. Currently, the sensors are just simple lines, so we would also like to create more advanced sensors in future versions of the simulation. Here are some that we have in mind. Vision-like sensors, which just extends the current concept of our sensor, but instead of having a line, we would like to have cone-like detection. LiDAR sensors, which provide a heat map of the depth in front of the agent, kind of like an Xbox Kinect sensor. In addition, currently our obstacles are static, meaning that they do not move. Later, we would also like to pit some artificial intelligence against dynamic obstacles. And by dynamic obstacles, we mean moving and morphing obstacles. We would love to see how a neural network would respond to this. Finally, OpenAI Gym is a popular environment interface used by many AI practitioners. We'd like to integrate our own environment with their library in the future to make it easier for others to plug and play with their own agents. Now that's all for today. Thanks for stopping by.